happy to talk with you about career opportunities afterwards if you're interested. But it's nice to see some old friends, some former students and colleagues. So as you can see, this is signal processing model of quantum mechanics. That's where our preprint is located. So I kind of been leveraging some of my background in electrical engineering. I mean, it's one of the nice things about unity of science. It's something we learn in some fields. May somehow turn out to be useful in a different field. And also I would like to say that I do like to talk interactively. So please, if you have questions, go ahead and ask as we go along. Don't think you can save it. You don't have to think you have to save it up until the end. I think that this it's very easy to get a wrong impression about what I'm talking about because I'm trying to think about familiar things in a new way. So I'd rather correct misimpressions as they come up rather than wait till the end and find out that you didn't understand what I was talking about all along. So please don't feel that if you don't understand that you're the only person. Probably a lot of other people don't understand. So please give us the privilege of asking you questions. But just jump in if you have questions. Right. So this is about a mathematical model of quantum mechanics. So what is a good model of physical reality? I'm primarily a mathematician. I do some physics, but I'm primarily a mathematician. So I'm going to tell you mathematical model. I mean, you guys model, but we really model. Okay? So think of this very complicated plate structure. It's a fern. I forget what it's some funny Latin name. And here's a mathematically generated fern. And you can see how close the shape is. Amazing likeness generated by some very simple mathematical equations. Okay? Those four equations generate this entire shape. Okay? It closely duplicates the form. Unfortunately, there's one small problem with this model. And the small problem is the way these equations generate the fern, the stages in the generation are like this. First, it generates this sort of cloud sort of shape, and you do some iterative. You iterate the functions, and it becomes more and more clear. And it becomes like this. Now, obviously, there's something wrong with this model. Ferns don't grow like that. The final shape looks pretty close, but ferns, I mean, it's not going to be. You've only got a final form that's similar. And the guy who came up with this said that he believes that somehow those equations are coded in the fern's DNA. And I don't really see how that's possible. Does the fern, when it's starting to grow, say, let me generate this shape in my memory, and then I'm going to try to grow into that? Okay? So what I'm trying to say is that mathematical similarity is not necessarily an indication that you have a good model. And what's missing is, although you have the final form, you're not modeling the process. There's something essential missing here. Okay. Are you with me with this? Okay. So tongue in cheek here. So I say mathematicians make good models. Okay. So it's not a satisfactory model. Okay. Of course, physicists never do this. Consider this the principle of least action. Now, I wonder if anyone else has thought about this. So here's a simple version of principle of least action called the principle of least time. It's really the very same thing, only with a different action. Okay. So what the principle of least time says, and light obeys geometrical optics obeys the principle of least time. Okay. If the light starts here and ends up there, it will take the path that minimizes the time. Okay, that's why light bends when it goes through medium. Because out in vacuum it moves faster, and here it moves slower, so you want to extend the time that's in the vacuum, and then it doesn't have to take so long in the slower medium to reach its goal. Now, beautiful model, beautiful mathematics. You also use this for mechanics, right? Hamiltonian mechanics, you can generate Hamilton's equations from the principle of least action. Really beautiful principle. So the system travels in the path that in the election. The problem is that to apply the principle of least action, you have to assume the starting point and ending point. Okay? So what that means, if you try to think of this as a process, the particle's thinking, where do I want to end up? Oh, I want to end up over there. So now I'm going to minimize the action, and that's where I'm going to go. So you see this principle really, it doesn't seem like it's a model of the process. It's got a mathematical similarity, but there's something kind of screwy when you think of a process that generates this mathematics. All right, so is this a coincidence? Is there something deep behind here? Does the light particle emanating from here really think about where he's trying to go? Tune in next week. All right, so could this possibly model the process? Okay, so I'm talking about bad models. Okay, so let's see about quantum mechanics. You've got the theory of quantum mechanics. Does quantum mechanics qualify as a good model? Okay. So historically, of course, there are two strains at the beginning of quantum mechanics. There was matrix mechanics by Heisenberg, and then there was a wave mechanics by Schrodinger. So I'm going to talk about wave mechanics. What Schrodinger said was, they had these funny experiments, I think Davis and Germer experiments, some things that seem to indicate that matter behaves like a wave. Okay. Now they already had this problem with light. If you remember way back in the time of Newton said that light's a corpuscle, a particle. And that was the primary paradigm for many years. And then Young came along with his diffraction experiment, and they said, no, light's a wave. And then they come around with photoelectric effect, and they say, well, gee whiz, we thought the wave. I mean, Newton said particle, now they say wave, now they say particle, and they can't figure out what it is. It's both particle and a wave. Okay. So Schrodinger is sitting in watching all of this stuff, and then they find similar phenomena with matter that seems to have both wave and particle. So he said, okay, light, we have this problem with light, now we have this problem with matter, let's see if we can solve it the same way. Okay? And when you deal with light, you have geometrical optics, which deals on large scale. You're not talking about small scale phenomena, so the wavelength doesn't come into play. But when you have small apertures or small distances, then you have wave phenomena coming. Okay? So he says, okay, let's do the same thing with matter. We know the geometrical properties of matter, Newton's law, all that stuff. Things travel in straight lines, they bounce around. So can we think of a wave equation that extends this geometrical mechanics in the same way that wave optics extends geometrical optics? Okay. Now, of course, he came up with this equation, huge success, and then the problem was, what did it mean? What was it waving in? They had this psi. What's this psi talking about? So they had to throw in the Born rule. Born rule says that the amplitude of psi squared is a probability. Okay. Now, doesn't this sort of strike you as kind of ad hoc? It's saying we have behavior, and we know how to make it work for light, and we'll try to make it work for matter too. And oh, by the way, we'll have to use this rule to make it work. Right. So there's really no process here. You're just doing a phenomenological fit to what you see. Okay. All right, now, of course, because we're all sophisticated, we have axiomatic formulation, and we know what's really going on with quantum mechanics. We know that the world consists of a Hilbert space of state vectors. Those are your wave vectors, right? And operators parse measurements are expectation values of self-adjoint operators. So now you understand what's going on. Okay, now it's all clear. This is what reality is. I mean, okay, you can axiomatize this, but there's something, I don't know if anybody else feels this way, but for me there's something unsatisfying about this. That matter I mean, Hilbert space is a complicated mathematical object. Why is this the fundamental mathematical object of reality? Now, you can just say, well, that's the way it is. And I think a lot of physicists do that. But I don't know, but I feel, and I think maybe some other people feel also, that there's something missing here. So I've been talking about, so where's the process? Right? I don't know if anybody recognizes this commercial. If you do, it dates you. It's 30 years old. Yeah. So where's the beef? So this was a commercial for Wendy's hamburgers, and they were competing with McDonald's. And this old lady was going to McDonald's and said, "Where's the beef?" So I'm saying, "Where's the process?" So here's an example of a good model. Okay, so this is the kind of thing I'm shooting for. So again, this is kind of qualitative way of thinking. You may not agree with me, but for me, this model that I'm going to talk about, it's a physics model, by the way, not a mathematical, so you can read easy. And it's very, to me, it seems very satisfying. And when I see this model, I think, you know, I really understand this phenomenon. And I'm talking about the kinetic theory gases. Okay. Now, you know you have PD equals NKT, right? And this is a phenomenological rule, the behavior of gases. And this follows beautifully from the assumption of moving particles, the elastic collisions, and the Gibbs distribution, which is a very plausible distribution when you talk about phase space and probability and equal probability of phase space. I don't remember all that stuff. Liebel's theorem and stuff like that. But it's really as a very beautiful derivation, very natural derivation. So you have this phenomenological law, very regular law, and it follows from this detailed picture of what's going on. And really, when you think about it, when you think about gases this way, it completely changes your view of what a gas is. I mean, imagine what the Greeks thought was out, what they breathed out. Just something continuous, something, or I don't know if it's something or not, but now you have this mental picture that this is billions and billions, or more than that, Avogadro's number of particles that are moving around, bouncing off, and in a way it's very complicated, in a way it's very simple, because the dynamics of the individual particles is very simple, follows Newton's law, conservation of energy, all that stuff, and follows very naturally. So, to me, this is an example of a really nice model, a really nice theory. And if you feel the way I do, it gives you the feeling you understand better what's really going on. Now, of course, that's not the ultimate reality. You know that particles aren't Newtonian particles, and there's a lot of complication below that. But it seems like you've kind of moved aside the curtain, and you've gained some kind of insight into physical reality. Okay. And another thing about this model is it leads to significant predictions that are apparently totally unrelated, like Brownian motion. I mean, if these really are molecules, then you expect some kind of statistical fluctuations because of the variations in the motions of particles. That if you have a small particle and it's being hit by molecules, it will have some kind of irregular motion. Okay. So this is kind of what I'm shooting for. I'm shooting for a model that will take phenomenology and it will give you some kind of underlying process. And also lead to some kind of predictions. You know, I don't know if I've actually come up with this, but anyway, this is what I'm shooting for. All right, so let me just mention some other quantum weirdnesses. Collapse of the wave packet, as you've probably seen all this stuff in your front course, that measurement has a mysterious effect on the system. You've got the system in a state, then all of a sudden you measure it, and then boom, it's in a single state. And there's a lot been written about this that I don't know about, but anyway, it just seems kind of weird. Okay, the EPR experiment, which says that you can have two events that are space-like separated. They're not time-like separated, so there can't be any causal relationship between them, and they're perfectly correlated. I'm not going to go into that in detail, but you've probably seen that in your quantum course, or if you haven't, you will. Okay, and one effect which says that. If you have a field that's completely isolated, you can never have a particle detection error. That field can affect the detection somewhere else. I don't remember what it's something like you have a solenoid, you have the field inside the solenoid, and all right. Well, I won't go into detail, but it's another one of these really weird things that happens with quantum mechanics. It's seemingly inexplicable, and the usual approach to this is shut up and calculate. Don't try to worry about why it's doing what it's doing. That's what the math says, so we'll just go with math and don't worry about any of this other stuff. And this guy is David Mermin, the quote originated from. People always say it's Feynman who said it. It's not true. People say Feynman say everything because he's so quotable. All right. So this is just some weird things, and I believe that the model that I'm going to propose does address all of these. And you can decide for yourself to go. All right, so what I'm going to do is I'm going to, and for most of this talk, I'm going to be specific to a very simple case, and this was my paradigm. You have the usual two-slit experiment. And you know how this works. You've got a source of electrons or photons or whatever. You cover one slit, and you get a single bump diffraction pattern. You cover the other slit, you get a single bump diffraction pattern. you uncover both slits, you get some kind of motional wave diffraction pattern. It seems paradoxical with the idea that there's a particle, because you'd think if there were particles coming out of here to go through one or the other, and you just superimpose the two distributions. So you know that you don't get superposition here. When you add those two, you get interference that you wouldn't anticipate from opening either one single. One thing is that when I was talking about the Born rule, that what happens is the probability of a detection anywhere on this screen is given as the squared magnitude of a complex wave function. Okay, there's a continuous field that gives the probability of discrete events. So there's this interplay between continuous and discrete that we call quantum. So I'm going to look at this. So one thing, I just want to ask this question: are there any natural processes that we know and understand better that exhibit some similar type of behavior, where you have a continuous field that determines the probability of discrete events? So I was thinking about this. So one example is lightning. I mean, you think about lightning. You have the ground, you have the cloud. What happens? Like this is some kind of static electricity, something like that. Is that right, Tony?
Yes.
Yeah, and there's because the air is rubbing against the ground, so you get charge separation. And this charge separation builds up fields in the atmosphere. You get these things called stepped leaders, and then you get a discrete pulse of energy moving from the cloud to the ground. So definitely there's a interplay here between continuous and discrete. You've got this continuous field that's mediated by this buildup, and then boom, you've got a discrete transfer of energy. Okay. All right. So and of course there's a lot of differences between this and quantum mechanics. For instance, in quantum mechanics, certainly you can have a variety of lightning strikes. Lightning strikes don't have all the same energy. You can have multiple lightning strikes, et cetera, et cetera. But just on a top-level view, this kind of process could be characterized as an accumulate threshold process. And you're accumulating to a certain point, and then once you reach a threshold, something dramatic happens to the system. Another similar behavior is seen in nerve transmission. Within the individual nerve, there's a buildup of ions, and then once you reach a certain point, then there's depolarization of the membrane, and then you get a pulse. But again, there's continuous field, and then once you reach the threshold, you get some kind of discrete behavior. So I'm going to propose a different model, which is kind of along these lines. It certainly can be characterized as an accumulate threshold process. So again, I'm specializing to one individual quantum detection, and I'm going to model that as through an accumulate threshold process. Oops. All right. Yeah. So that's my question. Can we model quantum detection as the outcome of accumulate threshold process? Okay. So my background, my professional background before I became academic again is in wireless communication. And while I was working in wireless communication, I noticed some interesting parallels between what I was doing and what I had learned in quantum mechanics. All right, so here, let's just leave quantum mechanics aside for a moment, and let me give you a scenario that you probably can understand. I can understand it well now, but when cell phones first came out, of course, when cell phones first came out, you often didn't get a signal. You get these dead spots where you couldn't get a signal, and that's because the strength of the signal varies throughout space. Okay, so imagine this scenario where you've got your cell phone. Here's the transmitter transmitting the signal, and you're moving around with your cell phone, and you're trying to get a signal. Okay. And so you keep moving it around. Now, what happens in the cell phone, when the way the cell phone acquires a signal, is that there is an accumulate process. There's an oscillator in the cell phone, and it's looking for a certain kind of signal, and that oscillator accumulates signal until it reaches a threshold, and then when it reaches the threshold, then it says, okay, I've located the base station, I can now communicate. So imagine a process where you have a cell phone, you're walking around, you're trying to acquire a signal, and of course the strength of the signal is varying. Now it turns out, interestingly enough, that the signal of a AM signal, the AM signal can be described as a complex amplitude. And I'll show that in the next slide. So here we have a complex continuous function that's sort of reminiscent of the wave function. And of course the signal strength varies with location. So the cell phone accumulates the signal until a certain threshold is reached. And when the threshold is reached, a detection occurs. Now the interesting thing, now you get this picture now. Okay, you're moving around, and actually, I mean, this signal is very, very weak. So you have to move all over the place before you can get a signal. And then cell phones accumulate. Finally, when it reaches the threshold, then it will say, okay, I've located the base station. Now, interesting thing about this, what's the probability distribution of the location of the cell phone at the point of detection? So again, I'm doing this over a very long time. That cell phone is moving all over the space hundreds and hundreds of times. What's the probability distribution of the location of the cell phone? And the answer is the square of the complex signal amplitude squared, which is just like the formula. So I thought, well, this is interesting. Can we do something with that? Let me give a little more background. When I say that a AM signal can be described as a complex amplitude, what you have is when you transmit signals, you have something called a high frequency carrier wave, and then you actually have cosine and sine, so you have two versions 90 degrees out of phase. And you can multiply the cosine by a low frequency envelope and the sine by a low frequency envelope, and you add those together. And essentially, mathematically, you can describe this as AMT plus IBMT. Basically, it's sine because it's 90 degrees out of phase, that introduces your I. It's just like in the complex plane, I is 90 degrees out of phase. So this is where the complex field comes from. And as far as signal strength varying is concerned, what happens is you get dead spots because your signal is bouncing off of what we call multipath. Where you have trees or buildings or whatever, and they're bouncing off regularly, and they come together at the receiver, and they may interfere constructively, they may interfere destructively, and depending on the way they interfere, and that determines the signal. So this is the kind of picture we have. So keep this paradigm in mind.
I never use cell phone, but my understanding, if I had a transmitter, let's say, the transmitter has a power for 5 transmitters. All the distance inside 5 transmitters, I should receive the signal. It's like a key.
Well, it is continuous, yes.
Yeah, but if we apply this to the output, it's like the operator.
Yeah, okay.
So this is like a quality complex difference.
Yeah, yes, there's a big difference. Okay, and I'll get to that. Okay, this is an analogy. Okay, so you can't. Well, you'll see if I'm successful. The way I'm going to carry this over will address this question.
Philosophically, these two models, quantum mechanics and your model,
yes,
are completely different.
Yes.
The similarity is because the Fourier analysis, and we have some sort of Heisenberg uncertainties in classical electromagnetism because of the, for example, in Fourier analysis, if you go to, for example, momentum space, if you have a peak in the position space,
yes,
you don't have this peak.
Right.
You have some sort of Heisenberg uncertainty. But philosophically, these two models are completely different because in quantum mechanics, the system before measurement is undetermined. But in your case, if you can't determine the position of the system, it's because of you have the lack of our knowledge. But according to Copenhagen school, I mean, the system is undetermined. It's not due to your lack of knowledge. Nature
I understand. I
And
understand.
so these two different philosophies are different. Mathematically, maybe they are the same, and we can say mathematical formulation.
Well, I can say a couple of things. One is that Fourier analysis does not mandate that the square of the wave function is a probability. That doesn't follow from Fourier analysis.
How do you
Another thing I can say is that the Copenhagen interpretation is non-deterministic. But does that mean the Copenhagen interpretation is right?
According to Heisenberg, at first Heisenberg believed that this is the nature of Fourier analysis, and Einstein
Yes, I
agreed with Heisenberg.
Yeah.
But after that, Heisenberg interpreted this thing as undetermination of relation.
So it's an interpretation, right?
Yeah.
But so it's just an
This is
interpretation.
why I told you.
Yes, but see, there's more than one philosophical approach to it. Because, well, you'll see how I apply this. You'll see it. I mean, I understand your objection, or I think I understand. And you see how I carry over this analogy, and then we can talk and see if it's still. Let me tell you that something that I'll get to later is that actually these paths that I'm talking about, I'm going to make a connection between these paths and Feynman paths. So you know there's that Feynman integral approach to Feynman. I'm taking that approach. And also at this point I'm just talking about making a spatial measurement. Okay? If you make a momentum measurement, then you would have to apply the wrong difference. But at this point, I'm just talking about the spatial measurement. But thank you. That raised some very. Okay. So here's the mathematical formulation of my. Again, I'm going back to my model. Not in the quantum mechanics yet. We're just doing this model here. Okay. So what I have is a modulated carrier wave. So like the picture I showed you, like that. And it has certain random characteristics. There's interference produced interference produces variations in signal strength. Then there's a moving detector that samples all possible locations. The detector consists of an undamped oscillating circuit whose natural frequency is the same as the carrier frequency. And detection occurs when the detector's amplitude exceeds a fixed threshold. So that's the mathematical background. And in the paper, I don't want to bore you with all the mathematical details, where I actually proved that Born formula. All right. So there's some similarities in both cases. So let's try to make a connection with quantum mechanics now. Okay. In quantum mechanics, you have a complex function that describes this. You also have a complex function and the square of the complex function is associated with a probability. And you also have discrete detection events. And of course, like you said, you can't actually locate the detection exactly, but I'm not going to the location of the detection exactly. But let me pass over that for you. Now, of course, in my model, I only had the cell phone have a spatial detection. Okay? In my model, I said that the spatial location of the cell phone is equal to the squared amplitude. Let me say that again. The probability of location for location of where the signal detection takes place. I was just talking about spatial location, not location in space-time. Okay? But you know that, of course, quantum mechanics talks about events located in space-time, not just in space. So my solution, and this I think there's a real changeover in thinking that has to take place here, is that I'm going to introduce another dimension for the process. Here I had accumulating in time as the cell phone moved around. But since I'm trying to model events in space-time, I need to accumulate in a separate dimension, not in time. And I think that when people look at this, they get confused because they think that that I'm trying to accumulate time. I'm not. I'm introducing another dimension. There's a process in this other dimension. And what I'm saying is that quantum detection is the outcome of a process in another dimension. Now, this is no great shakes, right? You've got M theory, you've got string theory. How many dimensions do they have? 17 dimensions. So give me one, okay? Give me one dimension. And you'll see what type of problems it solves. That's the corner I'm going to turn here. Is that in quantum mechanics, I'm going to accumulate in another dimension. Okay. So I did want to make it clear that the cell phone in this model, and this is another thing that I think people get confused about, is the cell phone in my analogy does not correspond to a particle. The cell phone corresponds to a single detection event, not a particle. So an analogy I like to use is a firefly. Suppose you're standing in your backyard and you see a firefly. You see a flash here. And then you see a flash here. And then you see a flash here. Then what do you say? You say, oh, there's a firefly traveling across who's flashing. Now, how do you know? There might be 3 fireflies. As far as you know, this guy sees that one and he starts flashing. So you see that this is the same situation we have in quantum mechanics. All you have are the detections. You don't know what's happening in the middle. So people have this idea of particles. So between detection, there's a particle traveling in. But how do you know? What I'm saying is that actually there is no particle traveling in between. There are only the detections, and the detections are correlated. And this gives the appearance of a particle traveling. And I think it's covered over there, but I haven't really worked this out, but I think this may have something to do with the statistics of identity particles. Because that what we call statistics of both statistics and Feynman statistics is kind of an artifact of this picture that these are different particles. But in fact, they're just events.
I'm sorry. So in quantum mechanics, you still have a conception possible. That's why you see my probability is conserved, because I found particle in the whole space of one.
Yeah.
No matter where I'm going to find, I will always find the particle.
Yeah.
But if you do not have particle, how do you talk about it?
All you need is conservation of probability. When you're talking about,
what's that mean for progression?
well, I'll just have to go on and you can see what probability is. Because you're not actually counting particles, are you? When you talk about conservation of probability, you have to talk about it in terms of detections.
Yeah, we talk about the probability of finding that particle and the certainty for the event, right?
Right.
So we still have the conception of particle.
Yes.
So that's why in the whole space-time,
Yes.
finding this particle is equal to 1. So if you do not have a particle, ours is how you do it. Philosophically, if you do not have particle, how do you detect particle? How do you talk about it? Finding.
Okay. So we'll go on. And I guess I should also point out that my understanding is that this probability conservation breaks down when you get to field theory. You get particles, you get hair production. So even in conventional theory, you have problems with that.
And then you still have the number of particles that you have to stick with.
Well, you have number operators and things like that. But I'm saying that that's a picture. But you have to get down to what just because it's a picture and it's a compelling picture doesn't mean that that's what's really there.
I have a question.
Yeah, sure.
What determines the density of detection events? Like, for example, in the conventional model, we have the particles actually exist, regardless of their interactions or whatever. You're saying that all we actually can talk about is the detection events. Well,
yes.
What determines the density of detection events? What happens, and what determines we have more detection events now as opposed to some other place or some other time?
Well, there are two things that I think you're talking about. You have quantum mechanics gives you a probability density. And that probability density means that It's a statistical thing. You may have more detections at one time or another just because of statistical fluctuation. Right. If you say what determines the statistical fluctuations, quantum mechanics can't answer that either.
Well, no.
But here,
so
are you talking
much-
about what determines the change in the field itself?
No, not so much that. Maybe go back to the fireflies or your cell phone model. I mean,
Right.
How many cell phones are out there getting ready to trigger? I mean, our picture of the world has been changed just depending on how many of these cell phones we have out there ready to say, oh, I found a signal.
That's true.
And so you.
All right, let me just start with one.
Okay.
Because I want to look. I mean, you have to build up a model. I'm going to start with one single. I'm just looking at one single detection event.
All right.
There's certainly a long way to build up to. I mean, you've got more than one event in a year. So, but let me try to get one.
Okay.
And then we'll go from there. And if you want to know the distribution for that one event, that's just going to be your wave function. Right. So let's see. Right, so here's my formulation of for a single quantum detection. What I have is a modulated carrier wave. So this is similar to my cell phone model. Only this carrier wave is not traveling in time; it's traveling in this other dimension. So the whole process is taking place in another dimension. So these carrier waves propagate in the other dimension. The interference produces variation in signal strength at different space-time locations. Remember that in my cell phone model, there's variation in space location. In this case, since my process takes place in the alpha dimension, I have variation in space and time. There's some kind of moving detector that uniformly samples all possible detection locations. So you can imagine that there's some kind of, I call it a detectron, that's moving around at the possible locations where detection can take place. This detector consists of an undamped oscillator with natural frequency omega. It's driven by the received signal, and the detection occurs when the detector's amplitude exceeds a fixed threshold. So again, this is a model of a single detection, and when we do this, we do get very close agreement with here. So this was a statistical thing. Right. So apart from the drawbacks that you've all mentioned, that I'm only looking at one event and there's other things going on, I have two things going on in my model. The model fails to explain where the field comes from. There's this transmission field. There's also this thing that's moving around at the possible detection sites. So is there any way to combine these two aspects in the same feature? So here's where I can refer to the Feynman integral formulation. What Feynman integral says is the propagator, the propagator basically gives the influence of one field point on another field point. And the Feynman formulation says that you can give the influence, so I should say, that's the influence of the wave function at one point on the wave function at another point. And that influence is given by an integral, a path integral of that quantity there. This Q of t is a Feynman path, which is a really crazy path. I used to think that Feynman paths were like Brownian motion paths. They're not. They're much crazier than that. Feynman paths can jump from here to infinity. They're just within one delta t. They're everywhere, and they jump everywhere. They're really crazy paths. But anyway, this works. This integral means I sum over Feynman paths, and this S Q of t is itself an integral. It's an integral along the path of the action. So that's the Feynman formulation, and you can use the Feynman formulation. I mean, they're both written about this. This is standard stuff, and it's accepted theory that the Feynman picture does give you dimensional quantity. What I could say that what this theory does is it puts a process in place that explains the Feynman formulation. And now I explain these paths Q of t as real paths that are being realized in this other dimension. That in this other dimension, as the system varies, the system is actually assuming these different paths as you vary the other dimension. Then as you vary over a long enough time, it samples enough paths so that the result becomes an infinite. I'm also saying that
if you introduce extra dimension, what's the scale difference space or some space, focus space or different space? If you introduce one dimension, different space.
well, I think that once you do the I think that Hilbert space comes as a result. After you do this process, you get objects that can be considered as elements of Hilbert space. That this process generates elements of Hilbert space. These paths themselves, I don't think
Word of paths, there's a key extra reference a word of paths.
yes, that's right. That's right. I have a picture that may show a little bit.
So you are introduced on top of that minor dimension.
Yes.
So I wonder what's that extra dimension, how that incorporated to the TX way we currently space time.
Okay. Maybe the picture that I'll show. The other thing that relates this to the cell phone picture is that this term here, if you consider this term here, the e to the I s q of t, that just corresponds to a phase shift on the carrier wave. As I mentioned, the carrier wave can be described as a complex function multiplied by the carrier wave, and this if you multiply by e to the is, then that's just a phase shift. So I can say that this is saying that each different one of those Feynman paths has a different phase shift. When you add them together, you get interference, which produces the ultimate accumulation. Now, the connection I want to make is that these, as I said, these Feynman paths are really crazy. In my cell phone picture, the detectron, or the cell phone, is itself jumping around in a crazy way. So can I identify these Feynman paths that accumulate and form the field? Can I identify these Feynman paths with the detector? And in fact, the way we worked it out, so you can, that you have two processes happening at the same time. The field accumulates, and the detection and the detection problem, it also accumulates at the same time. So let me see if this diagram helps a little bit. This is what I call a blip. So you take one single path Q of t, so this is path in time. It makes a contribution to the field at a single point, which is proportional to this term in the Feynman interval. And simultaneously with causing an incremental change in the field, it also increments the overall signal detection interval. Okay, you implement those, you do those both at the same time. So here's the picture that really sums things up. Here is my other dimension. As I vary this dimension, at each alpha slice, I have a universe. So I have x and t versus the alpha dimension. So I call these pre-universes. So in each pre-universe, you have one of these paths. one of these Q of t's, which is fine because I have x, y, and t. So that's where the path lives. The Q of t actually lives in a space-time. So in that space-time, you have this path which produces this accumulation. It accumulates both the detection signal and it accumulates the field at the point where it passes through. So you have a process that both accumulates your psi and it also accumulates the detection signal. Once you reach the threshold, then this is the universe that we see. So the detections that we see is outcome of a process where you get build up. The fields, these fields that are represented by these arrows, build up over the process, and then the result that we get. What we actually see is this red line. But the configuration of the red line, the location, depends on the entire process. So we did a simulation on this also, and so this is a two-slit experiment, and we're just doing half the screen. So this is just showing the nodes on half the screen. And we get, and of course the smooth curve is a theory, and the jagged curve is what we get. We ran this for several days. As you can imagine, because you're summing over these paths and they're very non-differentiable, it takes a long time to learn. Now, one thing that's interesting is that although there's a close fit, you get more detections here than you'd expect from quantum theory. So this is analogous to, as I said, in kinetic theory, you get effects due to the statistical nature of the gases. So if I can make any prediction that varies from quantum mechanics, it would be this. That this theory predicts that there would be some kind of raising of the detection probability in the nodes of the interference pattern.
So this is statistics in a little different sense because your statistical signal is significantly different from the smooth prediction.
Well, yeah,
Is that what the envelope is?
Yeah. Yeah. Now, one problem is that I cannot predict the size of this effect. In just the same way that you couldn't predict the size of Brownian motion unless you knew how much energy each molecule had.
The experimentalists would then ask, what sigma effect is this? Is this a 1 sigma deviation, or 2 sigmas, or 5 sigmas?
Yeah,
the error bars have a certain significance.
Yeah, I think because the deviation depends on parameters I can't measure, I can't tell.
How did you generate the envelope with dotted lines?
I used one discretization with one. I mean, there has to be some kind of discretization scale. We just chose one. It was fairly small, and then we could run it. If I make that discretization scale smaller, then the effect will be smaller.
Okay, so those aren't statistical.
These are statistically.
So if you ran the simulation again, it would be likely that your new points would be somewhere within
Yes,
the
yes, that's right. I'm sorry. Yes, these are. And here I just used the Poisson distribution because that's what it is.
Okay, so that's 1 sigma.
So yeah, I believe this is 1 sigma. This is 1 sigma. Right. So that's the point. I mean, if you look, I mean, it's clear that it should be higher. If you
Yeah,
look
if you want to say that it's a statistically significant deviation from the accepted prediction, then you have to say, here's my error bar, and it's 1, 2, 3, 4, 5. Here's my data point, and it's 1, 2, 3, 4, 5 sigmas away from where it should be.
Yeah. Well, I mean, if you're doing experiment, you would be operating off of that smooth curve, right? So your deviations would be from the smooth curve.
Yeah.
And I can't tell you where my curve will be because that depends on how big the discretization.
If you ran it forever and not forever, but you ran it next to forever, all those envelopes would get smaller and smaller and smaller.
Yes.
And eventually statistically significant statement
Yeah.
to say that your model gave some
Yes.
different than a straight line.
Yeah. So if the effect is there, you put it in. Right, so I think that's the best I can do right now, is that to verify this model, that's what I would say to do. Look at the nodes of the interference pattern and see if you get more detections than you think. The nodes are not actually nodes, but there's some small statistical effect that's increasing the field. All right, so here's where I talk about, and there, of course, there's a lot here that I'm not talking about. So you talk about multiple events. So how do you deal with that? You can accommodate that by multiplying detection signals together. So you have different detections, you multiply the signals from different detections. One of the nice things about this approach is the fact that if you want to go to a field theory, all you have to do is replace the Feynman path with field theory. So you should be able to extend this to a field theory. And then all these other things that I don't talk about, gauge field test, U2, all that kind of stuff. I haven't really looked into that, but we're talking about a signal, and signals have polarization, they have modulation, and the different aspects of physical fields might reflect some different aspects of the inherent world.
Would it be accurate to say one picture would be there's a universe and each valued alpha,
Yes.
and then they're interfering?
Well, they're related to each other. They're kind of building on each other. The green here are the field. These green things are basically the wave function being built up. And this green from here, see,
Are they operating independently?
well, the green, the red are in the Q of T, the Feynman paths are in as far as I know. I'm not sure how they're related.
Yeah, well, it seems to me, right, in that picture that you might consider those as separate universes, that there's actually interference
There's
in our universe.
the relation that I need between these is the green fields are undergoing a process. They're being accumulated as alpha. So these green arrows are related to the green arrows. And the green arrows determine the size of the detection.
So somehow they are related.
They are related. They're not completely uncorrelated. So
You have a differential equation to describe the relation between one and another. How do you relate?
that integral describes the buildup.
But this usually does not see specifically how they relate.
No, it doesn't say.
You have to have a differential equation or something like that to tell us how S changes. Because if you give me this integral, this can be anything.
Yeah.
So now, which kind of server are you working with? If I work with quantum field server, I have like quantum field equations.
Yeah.
I need to have like equations to solve something with the solution to X.
Also, these equations are indeed what we did here is Bohmian quantum mechanics, because it's a realistic version of quantum mechanics. The extra dimension is the quantum potential that we use, and the passes are real passes, not like the
Yes.
Feynman pass. And indeed, it's a very brilliant idea that we use here, and it's a generalization of Bohmian quantum mechanics.
Well, it's not Bohmian, because Bohmian has particles. I don't have
But
any
you are
particles.
talking about pilot waves.
No, I'm not talking about pilot waves at all. That's very different. Pilot, he doesn't have, well, again, we can talk about that, but he has deterministic particle location. And I don't have any particles at all. I only have detections. There's some relation, but it's really quite. But I reinforce that for you instead. I think it's hard to. I'm running out of time, so I don't know the best way to answer your question. there's a combination of the theory requires action is given. And the other thing it requires is these paths Q of T jumping. And I don't have a dynamic. I'm just assuming that they're moving random. So the whole process is driven by random process. And the input, the physical input is the action. So there are some gaps here. What's important is that it does give a constructive picture of a wave function where the wave function does satisfy the formula. And it also has the potential to be expanded to a field action. Right. So the three weird things about quantum mechanics are addressed by this issue. There's no in this model. There's no collapse of the wave back here. It just reaches a threshold, and when your universe reaches the threshold, that's the universe that you saw. There's no collapse. Non-locality. You do have non-local because here at the end, you have this path. You can have non-local relationships between locations on the path. So the wave function itself satisfies locality, but detections can satisfy non-locality. Okay, and the Hanneroth-Boyd effect, since I don't have traveling particles, it really doesn't matter that the field somewhere else can affect particle detection somewhere else. So maybe David can sing it. All right, so here's some other. There are a number of alternative theories of quantum mechanics, including the De Broglie theorem that you talked about. You can spend a whole hour on this, but basically they're very different. The many worlds is popular with some people. And many worlds says that at every instant your universe breaks up into an infinite number of other universes. So you get exponentially increasing universes. But here I have multiple universes, but they're all in one dimension. So I think it's a much neater theory to that. And De Broglie, you have the particle has to follow a guiding ray wave, so it's kind of like the particle has intelligence. That seems a little bit odd. In transactional quantum mechanics, there's some mathematical difficulties. So in closing, there's this famous quote by Newton. He says, I seem to be like a boy playing on the seashore, where the vast ocean of truth lay undiscovered before me. Now, when I was little, my grandparents had a place on Cape Cod, and it always fascinated me that when the waves break on the beach, when the wave breaks on a beach at an angle, you see the wave running down the beach. It looks like it's an object running down the beach. It looks like there's a causality there. Like you see this wave here, right? So where it breaks here. The point of breaking runs along like that. So it looks like a causal string. It looks like something moving. Now, of course, it's not anything moving. It's a wavefront. The wave comes from out here, and it just has the appearance of something moving. And that's actually what this picture says about reality. Is that the cause is back here in the alpha dimension that we don't see. And what it produces is a result that looks causal. But the causality is from somewhere else. So I just leave you with that picture. So thank you. Thank you for your...
I'm a moderator. I'm happy to moderate questions.
I can't think of it. I'm racking my brain. So yeah, that's where I would go. I would look in the nodes of interference pattern and see if you get more detections than you would expect.
Is your statement that the probability is proportional to the square is that an approximation? Are there other terms? You do your
That's assuming discretization.
So that's the only approximation ways that we.
Yes.
If you do have a discretized system, would there be deviation from size square?
Yes, there would be. There would be. And the size of those deviations, that's the only complexity.
If your simulation is discretized, could that be a reason that you don't get the expected result here to know?
Yes, that's right. So what I'm saying is that physically, just like with gases, there is a discretization. You do have discrete motion, and that does produce higher order effects. So I'm postulating that the universe also has it.
So is that discretization in the alpha dimension?
Yes. Yes.
So you
got
by measuring it experimentally and comparing to a prediction, then you can set limits on the discretization.
Yes. That's right. That's exactly right. So that's the analogy. All right. Well, thank you.
Silence.